You're the last person I tell.
Can you just hit yes? I'm going to record.
So just continue.
We're all good. All right, everyone. All right, everyone. I guess everyone's forgotten the etiquette of being in person in a room, that you can't just turn the microphone off and keep talking. So welcome to the RSES seminar this week, a school seminar. First of all, I'd like to acknowledge the traditional owners of the land that we are meeting upon, which is the Ngunnawal people, and acknowledge the long history of stewardship of this land and recognize their elders and honor them, those in the past, the present, and ones yet to come. Next week's seminar is also going to be an in-person seminar. We have a out-of-town visitor, so this is going to be something very special for us. It's Michael Griffith, who is happened to find himself in Australia and is going to visit next week and tell us about monsoons. So, but now I'm going to hand over to Michael to introduce John in a formal way. Thank you.
Hi. So before I start, I'd like to remind everyone that we have a petrology seminar every Friday at 12:30, and we're coming back to in-person meetings. So if you're not on the list and you're interested to be, so find me after seminar or send me an email, and I'll add you. So the email is for that. Today we have John Mavrogenes, who's a professor here at ANU. He's been working for many, many years on the petrology and geochemistry of ore deposits, anything from sulfides to gold, PGs to pretty much anything. In the past 7-6 years or so, has been focusing more on the earth elements and critical metals in general. So I think that the stuff that you will show today will show us how much we know and how much more we still don't know. John is now part of ARC linkages on critical metals, one with Corresponder from Adelaide, and another one with Marco Fiorentini from UWA, also working in collaboration with GSQ and all kinds of other industry partners on all aspects of earth elements and critical metals, in carbonatites, hydrothermal ore deposits, and all of that. And on to you.
Thank you. Okay, so this is stuff that I'm showing, which is also work that Michael and Ross, who's not here, a number of my students have been doing over the years. So I shouldn't try to take credit for all of this. But I'm going to start with the definition, which is an interesting one of what they call criticality. So this is a new buzzword. We have critical minerals, we have critical metals, and this is one that I just liked from the USGS, but the EU has similar ones, and the idea is you plot supply risk, whatever that is, against economic importance, whatever that is. And you find that there's strange things like magnesium and phosphorus and antimony and bismuth, but the top of the list is the light and heavy rare earths. So this is the ultimate critical thing. And the reason it's so critical, and I'll talk more about this, is that we have a lot of uses for it, and most of the supply comes from one country, and that country can distribute it as they please. That means there's a supply risk, why it's the highest one on this axis. This axis is kind of hard to define, because I wouldn't have thought tungsten was the most economically important of all the elements, but something I find interesting, something I've always valued, is gold is about the lowest. Because actually, we don't need it. We're mining it like crazy. And what's interesting is you can mine gold forever, and the price keeps going up. There's no supply and demand. We have no use for it. And mostly we put it in, we lock it up in a basement somewhere. So what's the point? Which is why it sits down here. These things up here, we actually have uses for. So the idea is it's critical, and the Western countries need to find our own supplies, and we need to figure out how to extract it, and how to use it, because we have so many uses for it. And if you go to most talks about critical metals or rare earths, they'll show you something like this, where it's abundance versus atomic number, and show you that the rare earths aren't that rare. There's a lot of them. These other elements that I like working on, these are actually rare. Iridium, of course, would be the champion for the most rare thing on Earth. And these things are incredibly valuable, from $1,000 to $3,000, $4,000 an ounce. These things, as I'll show you in a minute, are worth much less. So why are they so critical? They're critical because we've got a lot of amazing uses for them. One of the things that's strange about them, and here's just a list of the rare earths, and sorry for the quality of this, it's just something I stole off the internet because it's hard to find the price of the metal anywhere. It's kind of secret. But the point I wanted to make is that here's January 16th, here's a year later. Notice here, the lanthanum and cerium, you're getting about $2 a kilogram. Can't think of much that's cheaper than that. I think salt would be a lot more. I'm sure flour's more than that. It's like, I don't know what's worth less than cerium and lanthanum. And what's strange about the rare earths is you never get to pick which one you want. If you have a rare earth deposit, you're going to have all of them, but they're going to be in varying amounts. And so there are no minerals that are just a gadolinium phosphate, for instance. That doesn't exist because you're not going to get it by itself. You're going to have all of these. Interesting. Look down the list here, and you see the first one you come to is praseodymium, $48 a kilo. Yes, Richard.
But there was Walter Crump III discovered that neodymium phosphate at a quarry in Texas.
That's trivial.
But actually, its name gives you the clue. It was Crump.
Well,
Infected.
wow, that's good to know. Thanks for that, Richard.
Well, Brad and I remember this because he was a student at the University of Michigan. When I was right there, they went to the lawsuit to remove his PhD because he fabricated thesis.
Well, that's a lesson to all of our PhD students, not to make that up. Right?
That's right.
So now, if we look down here, the next one's neodymium. There's $40 a kilogram. We're starting to get some value. We come down here, we find things like dysprosium, 210. And look at terbium, 370 in January 16, went up to 730 kilo. Now this is starting to be stuff you can make some money on. But it turns out that terbium is quite rare, and there's no deposits that are rich in terbium. So the idea here is that if we could pick a deposit with only certain rare earths, we would be thrilled, but we can't. You get them all and you deal with it. And what we need is what I'm going to tell you now, is we look at things that we use, and I won't go on about this because many talks on critical metals go on endlessly about it, but notice how all of these things are things we love. And magnets is top of the list. Magnets and batteries are the things that we're seeing in the future are going to be a big deal. And if you could predict the future, you would see a plot like this, where we have the amount of rare earth oxides that we're producing in metric tons, so many thousands of metric tons of them, against year. Notice how in the early years, we have the USA being the biggest producer. That's one deposit, one carbonatite associated deposit in on the border between California and Nevada, called Mountain Pass. Notice how Mountain Pass at some point closed down, and then look at this red, the big growth of one deposit in China, Bionova, which I'll talk about. So that this is why we say it's critical, because one country has control of most of the goodies. And if you look at the trends, unpredicted trends, they think it'll do nothing but go up. So we need more and more rare earths, especially for the green economy, yada, yada. This is for sure. It's not going to go dropping down by any way. And if you try to predict which ones we'll want, here's where we see that, for instance, pearl cerium. Here's 2020, 2025, by 2030, we're pretty much the same amount. But notice this blue one here is neodymium. It's going to go way up by 2030. So neodymium and dysprosium are the two ones we want for the future. And these are the things that we use in high temperature magnets. And we're going to make a lot of high temperature magnets for electric vehicles and wind turbines and everything else. So this means we need a lot of neodymium. And notice how lanthanum, pearl lanthanum, it doesn't really get much of a guarantee. So there's only a few that we're really, really going to want a lot of. And that's what we're going to have to go to some effort to catch. Okay, so deposits on Earth. There's really only, so far, two. One of them is this one called Mountain Pass, the one I just mentioned. And the other one is this one here in Mongolia. We happen to have a Mongolian person in the crowd. There she is. Right? So these are the two, Bionova and Mountain Pass. And notice how on this diagram, they're either a red spot or a green spot. The red spots are all associated with carbonatites. The green spots are associated with peralkaline intrusion-related rare earth deposits. So when it comes to the two big deposits, we only have 2 associations to think about. There's lots of other things, and if we look at this next map, we'll see that we've got uranium deposits, we've got, you know, laterites, placer deposits. These have been big in the past, mining sands for monazite, for instance. But, you know, all of these other choices, and many of them aren't real players. The biggies are these peralkalines and the carbonatite complexes. But you can notice how there are a lot of places on Earth where you find enrichments of rare earths. And so what we're trying to figure out now is look at all these spots in Australia. One of them here is in beautiful Dubbo. That's a place called Tungi, which is getting set up to operate right now. And it's interesting that Alkane Resources own Tungi, and they spun off a company called ASM, Australian Strategic Metals. And as a shareholder of Alkane, I was lucky to be given shares in ASM, and I didn't know what they'd be worth. And they immediately went to $2 and then $7, just out of nowhere, which means people are interested in the stuff that's in these. And notice, this is a strange one, it's in these peralkaline. So I'm really going to talk about these 2 styles of deposits, and I won't talk a lot about peralkalines, except to mention a current student and a former student, Ross Chandler and Carl Spandler, did a project on what they call the Peaks Range of central Queensland. And what they found was, it's funny that Ross was doing his honors up at JCU, and he drove by all these funny mounds, and he stopped and sampled one once, got it analyzed and realized it was full of goodies. So he did his honors on it with Carl. And you can see how there's a whole bunch of these bumps as you look up to Eastern Australia. And in detail, there's a bump. Look at that. That's the thing that Ross studied. He sampled tar out of it all across it, analyzed them up, and look, there's another one, there's another one. And most of the bumps you see as you go up Eastern Australia, the Warren Bungles, Mount Canoblis, all of those, there's some sort of volcanic activity that's related to plumes, and Rodney has famously told us about how and why they're there. So if you look at some simple plots, and you plot whatever against whatever, zirconium against thorium, right? Here's niobium. If we look at, let's say, lanthanum, as these things fractionate, the elements that don't fit into mineral structures accumulate. So they're incompatible. And if you fractionate it long enough, they get incredibly high. So these things aren't hugely economic yet, because you can see there's only, you know, 500 lanthanum. We could have maybe 1% of rare earths total. You'll see in the deposits that are making a lot of money, it's not 1%, it's many percents. But these are the future. We're going to be mining these things because they're full of a lot of stuff we want, including tantalum and niobium and you name it. Okay, so now I want to get to carbonatites. And when we look at carbonatites, of course, there's Bionovo. It took a long time to realize it really was carbonatite associated, because in the early days, they didn't know what the hell it was. I saw numerous talks in this 30 years ago where they weren't sure. Down here in southern China, they have rare earths that are adsorbed onto clays. They've made a lot of money extracting that, but that's becoming less popular because it's not very environmentally friendly and it's a bit of a messy business. So it's these sorts of deposits that we're going to talk about, and I'll briefly talk about a different one because I wanted to mention that if you look at most of the carbonatites of the world, they're associated with some sort of plutonic igneous rock that's usually like a nepheline cyanide or something like that, and that associated with them are the carbonatites. And so here's a deposit that's unimportant, but what I wanted to point out was there are veins coming off of these deposits that look very much igneous, and then there are veins that start to look very much like a hydrothermal ore deposit. So I work on a lot of hydrothermal ore deposits. The porphyry copper deposits that are associated with magmas have a lot of veining systems, and those veins are purely transporting the material in solution. They cool down, they precipitate that. So that we see disseminated ore, we see it in veins, and we see it in really igneous veins. So the question is, how igneous are these deposits? And what's strange is if you look closely at them, this looks very much like a sort of a gold deposit. You got a quartz vein with some minerals saturating in it. And so that this is making people think that these deposits might be hydrothermal. Question is that a thing or not? So let's go back to the big boy, Bionovo. Biggest deposit on Earth, it's huge. You can see the little flashing dot shows you that it's way up there in the middle of nowhere, near where Yaji comes from. And the funny thing about carbonatites globally is they're enriched in light rare earths. And look at this. I told you that you can't get even $2 a kilo for cerium, and that's what most of what they extract is. Now they'll sell it anyway because they're getting it out, but it's these other things we want, right? Some of these other goods, praseodymium, neodymium, dysprosium, those are the goodies we want. But notice here that it's 36 million tons in total, and it's 6% rare earths. So that's a lot higher grade than any peralkaline system, and that's a lot higher grade than anything but iron ore. No copper deposit is 6%. No gold deposit is 6%. That's really high grade, and that's what we're really on to make. So one of the things that's crazy and why it took so long to figure Bionovo out is it's a carbonatite that's hosted within carbonate. And so who would have thought that you'd have a bunch of dolomite and you'd intrude a molten carbonate melt into dolomite? Now that might just be fortuitous, or it might actually be important. If you look closely, and people have, and you map all of the carbonatite dikes and all the silicate dikes, and you look carefully within them, you see that there's a carbonatite vein, which is definitely magmatic, and then it has the phenite around it, and the phenite is a term that we use for alkali metasomatism around the carbonatite. So this is not uncommon. There's ore in the phenite, there's ore in the carbonatite. So the only rocks that are there hosting it are slate, which isn't very high silica, and carbonates, which aren't very high silica. And if you look close enough, you'll see dolomite with veins of dolomite. So this is the confusion of why people struggled for so long to figure out what this mess was and how it was made. So that's something to keep in mind, that we have them carbonatite melt intruding low temperature carbonates. So when we look at hydrothermal deposits, we like to look at fluid inclusions. So these are the little buggers here with a little bubble in it, and these are all fluid inclusions. So whether it's calcite or quartz, we double polish it, we can see into it, and we can see these high CO2 fluid inclusions, and they homogenize here at relatively high temperatures. So we're talking about 200-300 degrees temperature. That's not unusual for an ore deposit. It's something we see quite often. And there's a whole bunch of other deposits which are full of crystals. And notice how every one of them has a crystal in it. So the idea here is that we trap a single phase fluid at 400 degrees, and as it cools down, it gets denser, so the void is filled by a bubble, and the solution eventually saturates in whatever it is dissolved in it, and it forms what they call a daughter mineral, which is sexist, I realize, but I don't think son sounds very good. Maybe they should be progeny. Not sure what it should be, but these are things that say that every fluid inclusion has a crystal in it, and the crystal is there because it was dissolved before it crystallized out. So look at all these, and these fellows here, I'll show you the reference in a minute, H.R. Fan and his students, they broke a bunch of these open and put it on the SEM, and looky here, that crystal there has cerium, neodymium, lanthanum. That's quite extraordinary. So now if this really is a daughter mineral, and this really is a fluid, then that's got to be, I don't know, 20% solubility. Very high solubility. And so they kept doing this and showing that everywhere they went, there is a crystal of salt, and there's the rare earth phase, again, loaded with neodymium, cerium, lanthanum. So this again is telling us that this was a fluid at, let's say, 400 degrees centigrade, and that it was carrying that much in it, which means that rare earth elements are soluble in solution, and you can make a hydrothermal deposit, or so it seems. Okay, so here's some temperatures of those. They're as high as 480. That's high temperature for anybody's business. Any ore deposit that's hydrothermal ore deposit at 480 is high temperature. So in this, they said that having these things soluble means we could form Bionovo without requiring large-scale convective fluid systems and high water rock ratios typically envisioned for other magmatic hydrothermal ore forming environments. So that's just what I said, just reinforcing that if they're really soluble, we could do this with very little fluid. We just need to saturate a fluid in it, and then we can deposit in the crust. Everybody's happy. That's not the case with most other hydrothermal ore deposits. And if you look at the source, the suggested ways that Bionovo must have formed over the years, syngenetic sedimentary, no, I don't think so. Metasomatism associated with granite, no, right? exhalative, ocean floor stuff, no, they ruled that out. Some sort of multi-stage hydrothermal metasomatism, yeah, getting there, but they chose metasomatism by fluids derived from carbonatite magnetism. I don't think there's much argument about that. This is the way it is, right? Carbonatites are rich in rare earths. If you fractionate them far enough, they'll get really rich in them, and then you can do whatever you're going to do to make a deposit. Okay, so I was talking about daughter minerals, and this is from a student many years ago doing synthetic fluid inclusion, something we like to do here, where we had trapped a bunch of copper chloride bearing solutions, and as it cooled down, a bubble developed and a little crystal of copper chloride showed up. And notice how we know they're daughters, because they're all proportionally the same amount. And so we can take this on the laser ablation system, we can measure the amount of copper in the solution, and we can figure out the solubility of copper in a fluid inclusion. These we know are real daughters, and we know this was just fluid, no magma. So this is a very simple way to figure out that if you want to form a copper deposit, you're going to move a lot of water through a bunch of rocks and make a big open pit where all the rocks are bleached. That tells us there's high temperatures, very high water rock ratios. It takes a lot of fluid to make a copper deposit. Even though copper is readily soluble, it's rare to find a fluid that has more than 1% or something in it. So this is what we expect in a hydrothermal deposit, but that's not what we see in most of the rare earth deposits. So it's something different. Okay, so this is another study here from up in the Tanami. This is Carl Spandler and some of his students are working on this very odd deposit up in the middle of nowhere, which we're going to go visit fairly soon. When I say middle of nowhere, I'm not kidding. It's way up in this part of the world. And so in here, there's a bunch of these known as H3 prospects, which means these are deposits that are quite rich in heavy rare earths. And so there's a whole series of these deposits. You can see all of these stars, and they're sitting in sandstones above the unconformity. So the scary bit is, if you look at them, they've got breccias, they've got multiple veins with selvages around them, and within and around these veins, they have the mineral fluorensite, which is very strange because it's dysprosium aluminium phosphate. Now, most hydrothermal people think that alumina is not something we transport in solution very often. In fact, it's very hard to do that, right? It wouldn't make a good can to put beer in if it was readily soluble. So alumina is not something we expect. So something strange is going on here, and they're in with phosphates. Okay, so this is something that's suggesting this could be a hydrothermal rare earth deposit. And we're working on this. They're exploring for more. This could become a major rare earth district for Australia in the near future. Okay, so let's look into rare earth element solubilities. A number of people, including Willie Jones and Migdasoff, who worked with him for many years, have done a lot of solubility experiments. And in general, they found that the lights are more soluble in solution than the heavies, so that most of their plots are coming down to the right here. And that's sort of accepted, but we really don't know. So I'm going to go through a few different studies of solubilities. This is one that I had a visitor a few years back. Li Zhou, who was here for a year, did a bunch of experiments. And he made synthetic fluid inclusions. So here's a bunch of synthetic fluid inclusions that he made. And we used them on the fancy 157 laser downstairs. And this is showing you that we turn the laser on and we get a little bit of contamination off the surface. We drill through the quartz, we only measure quartz. Then we hit the fluid and out bursts all of the things that are really soluble in here. In this case, we put cesium and rubidium in to ratio the lanthanum to. Notice how the lanthanum doesn't come out immediately because it's in a little daughter crystal. So the solubility is proportional to the area under that curve. And we can ratio this to the rubidium or the cesium and get a really accurate measure of solubility. And what we found was rather interesting, that these are all the phosphates, lanthanum or yttrium phosphates, and we found them solubility as phosphates in ppm ranging from butterall to 3 ppm. So the solubility is not very high. This is not how you make a deposit without a lot of fluid. This is saying insoluble. And I want you to keep in mind that if you get into molality, it's something sort of 10 to the 5th, 10 to the minus 5th, right? That's a very low solubility. And all the experiments we did, as good as we thought they were, we found them to be terribly insoluble. And if you compare them with all the other folks, we can see that, yeah, okay, ours are sort of in line. We can get up to molarities of -2.5. That's still not great. That's maybe 100 ppm. And that in general, we're not quite in agreement. Like there's quite a range from 10 to the -5.5 to 10 to the -2. That's a big discrepancy. And we're not finding solubilities that are terribly consistent. So there are a number of ways to do this. And one way to do it is to do it on synchrotron. And so at what they call the FAME beamline in Grenoble, they have a beautiful cell that you can fill with solution, and you can run a beam through it, and you can measure the amount of whatever you're interested in that solution relative to a standard solution. So we did that, and what we found was that whenever we had phosphorus in there, phosphates, the solubility in ppm was, again, incredibly low, but when we just put in ytterbium oxide, look at this, we're getting to 16,500 ppm. Look at here where we just had ytterbium silicate, we're up to 36,000 ppm, and then back to the phosphates, nothing. So this is indicating that if you have phosphates, it makes them insoluble. And this sort of fits with what we think of in terms of mining monazite from a beach sand, right? If it was readily soluble, it wouldn't be showing up. It's there with zircon and garnet and things that aren't going to go in solution. So this is a problem because if we're going to make a hydrothermal deposit, we can't transport it with phosphorus, which makes the minerals, we're going to be in trouble. We're going to have either fluid mixing or phosphorus at soar, whatever. Okay, so there's fellows at UCLA that have done a whole bunch of really interesting experiments where they take a crystal, in this case monazite or xenotine, take a crystal, put it into a capsule with a solution, weigh it really carefully, run it at a pressure and temperature, take it out and weigh it again, and figure out how much it lost, and that's its solubility. So it's a different technique, but a valuable one. This is showing some of the crystals afterwards. You can see how they've been etched. So they've been partially dissolved. You can see that on that surface there. And they found solubilities that are, you know, kind of like 10 to the -3, 10 to the -4. Again, not terribly soluble. So my point out of this is to say that if we want to make hydrothermal deposits, we sure don't have any data saying that it's a readily doable thing. We got a problem. They're not soluble. Okay. So now I'm going to get to Michael's crazy experiments. And I won't say that much about them because Michael should really speak about this because he did all the hard work. I'm just here to tell you about what's interesting of it. Okay. So let me start with this one. This is Michael's favorite crazy diagram. 4 experiments where we put carbonatite into a capsule and let it crystallize from 1200 down to 200 degrees. So that we're doing a sort of a magma chamber experiment, sort of Bowen's reaction series for carbonatite. And the idea here is that all of these crystals that are forming are crystallizing at high temperatures. And as we go into the center, we're going down temperature. And I'll show you, I'll explain that more to you. But this one up here is just carbonatite with nothing added. So we took a dolomite and calcite and some lanthanum and some dysprosium and some chlorine and phosphorus and a few other things lying around, chucked them in there and crystallized it out. This one has silica in it. So you can see down in here that we're starting to get other minerals like biotite, and clinopyroxene. And this isn't unusual for gonoplanetite when it's involved with a lot of silicon. But the most interesting ones are these, one where he added sodium and one where he added potassium. And notice how we got, again, all the same crystallizing down into, we got at low temperatures, this black field, where there's crystals growing, and then there's some sort of red muck that has precipitated out, and that red muck is very, very rich in rare earth elements. Okay, so this red stuff is this sort of composition that has everything in it, including quite a bit of dysprosium. So he only put in lanthanum and dysprosium, and looky here, this red stuff is incredibly rich. We believe that this must have been in a fluid that was surrounding all of these crystals, and then at the moment it quenched, that precipitated out. So that's telling us that at 200 degrees, we can have some considerable solubility, the rare earth element. Certainly dysprosium here. And this is an interesting thing Because if you take the red pixels and divide them by the black pixels, you come on a solubility of 3,000 ppm. That's orders of magnitude higher than we've ever measured before, which raises the question, is there really a hydrothermal rare earth deposit, or are they simply associated with these magmatic systems, and if you're close enough to them, the fluid / melt that might be coming out can transport them to a limited degree, but not very far. In other words, we're probably not going to just go out over hill and dale and find a hydrothermal vein of dysprosium. It's just probably not going to happen. Okay, so the good news is that Michael made a beautiful cartoon here. So this is the carbonatite. This is carbonatite with silica. This is the sodium and potassium ones without and with silica. And the key thing here is that when silica's around, it changes the minerals you make, right? Silica allows you to force a lot of the rare earths into apatite, so that Nolan's Bohr, which we worked on, Michael did for his PhD thesis, all of the rare earths were originally in apatite because it was intruding into a gneissic silicate system that saturated it in silicon and forced all the rare earths into these beautiful apatites. And so if we look along here, what's really interesting is that if we look at the sodium-rich or potassium-rich variety that is intruding in an area that isn't high in silica, we can get significant rare earths into the phenite. And you say, well, where the hell would we have a carbonatite intruding into non-silicate host rocks? And I say, well, by an ogo. It's dolomite being intruded by a dolomitic carbonatite. It seems fortuitous, but it could be that the best thing on Earth to do, if you want to have a rare earth deposit, is to have a carbonatite come in and interact. I'm going to explain a little bit more. This pink stuff here with a little dash line, that's the melt. And then this ugly baby blue here, that's the fluid. So that he's saying that in this cartoon that, yeah, okay, we'll lose a little bit in the apatites, and we can have, you know, some other weird phases of light, but if you want to get heavy rare earths out into the country road in a phenite, this is the way to do it. Have an alkali-rich carbonatite that doesn't interact with a lot of silica and transport that on the wall run. If this is the case in all deposits, then this is telling us a lot about what we need to look for. We really need to look at phenitization. That's the process of alkali metasomatism around a carbonatite, right? That's going to be a real tip-off. And if this is true, then we're going to find rare earths within that phenite. So that this is not in the carbonatite, it's next to the carbonatite, but it's really close to carbonatite. Now, one of the questions we have is how far from a carbonatite could we go? And how far from a carbonatite could you go and know you were still carbonatite associated? Not an easy question. Okay? So this is the story that I really wanted to tell you. And I wanted to give it a sort of an analogy that I remember years ago working on copper deposits in sub-arc volcanic systems that are the so-called porphyries, where the intrusion comes in, there's lots of igneous activity, fluids exsolve out, it alters the rock around, and there are veins everywhere. And the veins range from really igneous to really hydrothermal and something in between. I remember 20 years ago yelling at Richard Arculus about why don't we have a word for something that's in between a dike and a vein? And it turns out just recently I've seen some publications where, guess what they're calling them, Richard? A vein dike.
I was going to say,
Right. A vein dike. What this means is that there's something in between an igneous and a hydrothermal. That it's if you look at them, there's too much in them to have been transported purely in solution, but there's too much hydrothermal in there to have just been an igneous thing. It's one of these strange quandaries that maybe there's something in between that is what's transporting this, and that this is the key to making a really high-grade rare earth deposit. Okay, so let me just chat a little bit more about this. If you want to find yourself a large rare earth deposit, you're going to have to look for a carbonatite or a peralkaline system. There's other ones, I agree, but most of them are not really big. You're not going to make a lot of money on it. How far from igneous source? That's not an answer, that's a question that we need to figure out. So we need to take those solutions, whatever the hell they were that Michael made, we need to trap them in fluid inclusions, and we need to study them and see how dependent they are on being really in touch with carbonatite. In other words, yes, they're very rich in CO2, But is it CO2 dissolved in water, or is it some sort of carbonic thing? We don't know that yet, right? So deposits with no connection to magma, is that even possible? Will we ever find that there is something that can transport rare earths in solution without a magmatic component nearby? I don't know, that's an open question. Something we're gonna work on for years to come. And then this idea of here is how do you tell the difference? When do you switch over? The folks in the porphyry world talk about the magmatic hydrothermal transition as if it's a place that you can go put your finger on. It really isn't. Even they would admit that they struggle to say where it happens. You can follow veins in porphyry systems where they do seem to appear to be mostly igneous and then mostly hydrothermal. And when I say hydrothermal, I mean in a porphyry setting where it's mostly quartz. So you look at a gold deposit, it's a quartz vein with a little bit of gold in it, right? We don't have rare earth deposits like that, where it's a quartz vein or a carbonate vein with just a little bit of rare earths. So what are we looking at? And then more importantly, what are the complexes? People will say that chlorine, CO2, fluorine are important components for transporting rare earths. But just alone, we haven't been able to get them to make them highly soluble. Is it a combination of all of the above? Or is there some weird complex that needs alkalis so that we're making some sort of strange molecule in solution? Yeah. I think that's as far as I'll go there. I'm happy to take questions.
All right, so those who are participating remotely, flag it on the chat that you want to talk. You might even be able to unmute and ask the question. We can try that. But in the meantime, we'll ask anyone in the room.
Yes.
So, first, thanks for a lovely talk. So you mentioned your first point there was that to create the deposits, you need to be carbonatite, sulfur. Can you say a little bit more about what type of regions you find them, or potentially the processes that create carbonatite?
Wow, interesting question. Why do we make peralkaline magmas? There seems to be two schools of thought. One is we can just take your run-of-the-mill plume and fractionate it far enough and it might get there. Another is we have to have special subcontinental extract minerals that have been previously metasomatized to give it just the right composition. I struggle with that model a little bit because it seems fortuitous that we would say, oh, trust me, there's this layer down there that if you do the right thing to it, you get everything you want.
Yeah.
But these are the two schools of thought, and I sort of sit in between on the peralkalines.
So peak range is interesting, right? Because it's on the age progressive track, but it's also quite close to a step in atmospheric thickness. So is there a potential link there?
That'd be fascinating if it was, and I hope that.
So do any of the others around the world potentially show that same combination, or they?
Yeah, I don't think we know enough. Richard, any thoughts?
But I mean, the stock answer to Roger's question, where do you find peralkaline complexes and carbonatite would be, a rift. For example, the world's only active, more or less, carbonatite volcano, so presumably sitting on top of a carbonatite system, is Aldonia Lengai in East African Rift, due west of Kilimanjaro. So I think a lot of people hold that in mind. And then it's a question of, well, with an ordinary mantle source, even if you melted only less than 1%, and imagine you could get that melt out because you're sitting in an extensional environment. Would you get enough rare earths from ordinary mantle source to make sort of a bunch as you see? I think a lot of people struggle with that. So, well, not really. What you get to 10%, not get more.
But to make it even worse, Richard, to make it even worse, that sitting under Africa is a big plume. Some people suggest it's more about the plume than it is about anything else.
Well, and some of the world's biggest atmospheric thickness variations as well.
Yes, absolutely. It would be neat to know the link of what, and why kimberlites and carbonatites show up where they do, right? Obviously, diamond-bearing kimberlites have to come from thick lithosphere, but why they occur where they do? Yeah.
I think we should bring a carbon expert in here, like Greg. So how would you answer that question, Greg? Why are these carbon dioxide rich systems found where they're found?
I don't know.
Well, I don't think anybody knows.
Well,
I don't think anybody knows.
Unsaturated silicates.
Yeah.
Why they put it
Yeah.
So that's what you
Yeah, yeah. So these are all open questions that I think we have to explore.
Yeah.
And, you know, I'm hoping that you're going to give us the answer, Robert.
Well,
Do we need a step?
Mark loves fast.
Excellent. Good. I'm glad you could get here. Welcome to Australia. Yes, Richard.
May I ask a question?
Yes, you may.
If you go stumbling around the countryside, such as Ross did, would you know that you're sitting on something really exciting, a carbonate full of rare earths? Or would you think, what a scruffy piece of material? I'm interested in things that look better, like a garnet schist or a nice basalt full of olivine crystal. In other words, there's just an exploration prejudice against recognizing what you're faced with.
Yeah, possibly. And to make it even worse, that if you march around Queensland long enough, you'll find that there's so much alkali metasomatism up there that it blows your mind.
Yeah.
And you'd get bored with it. So, oh, I'm sick of this phenites. I mean, where the hell are these things coming from? So no, however, it turns out that most of the extrusives up in northern New South Wales and through Queensland that Ross busted a piece off had very strange mineralogy. And they were something fishy. And there aren't very many of them up there. Like he went and sampled around the wormbuggles. And those are pretty evolved peralkaline systems.
He's a pipsqueak. How dare you go around walking on ground that say, I've walked across it, I don't recognize what it was.
Well, you got a lot of explaining to do, Richard.
Yeah, watch out, you'll get there's questions coming from the chat.
Okay.
So can I do a couple of those?
Yes, please.
We've got one here. What can you say about those rare earth deposits that are classified as unconformity related?
Yes.
I think that's just, you can be expensive.
Okay. So there's a type of uranium deposit called unconformity type that we see in places where you have thick sandstones overlying really old gneisses and things that have graphite in them. And the idea is that because uranium is so redox sensitive that we have these oxidized fluids coursing through the sandstones, and where they meet the reducing material, either reduced iron or graphite or whatever, they precipitate out. So we've got a bunch of them up in Arnhem Land that sit underneath that sandstone, and those are called unconformity type uranium deposits. So when Carl Spanwer and his students went up to Tenemai and found that it's a sandstone and it seems to be sitting above an unconformity, they made this an unconformity type REE deposit. So it's a tentative name that probably needs a little more exploring, but it's the same idea. It seems to be something to do where we have reaction between the fluids that are in sandstone and underlying host rock or magmas that we don't know what's below the unconformity. So we're going to have to go sniff around there. So it's a tentative name that's so far a pretty good one, but I don't know if we know really what they are yet.
Number one, was fractionation the only likely mechanism for the Tungi RE enrichment?
Yeah, that's a good question. I think it explains it pretty well. I think it really does. So that's the model we're going through, and there's a couple of good papers where people have gone through and said, look, we can fractionate most anything far enough, and we can find niobium, zirconium enrichments like Tungians. But there's other things. There's some immiscibility in there, some textures that Carl couldn't explain, nor can I. So there could be something fishy going on there. Anyone else?
Back to the room.
Michael? That's right. Yes.
So in you showed the image of peak ranges in these places that maybe Ross.
Yes.
And you have those kind of scummy little blobs.
Yeah.
Are the deposits only found with those blobs, or are they closer to the volcanic center itself? The peak ranges.
Yeah. My understanding is if you go away from the blobs, you mean just the country rock?
No, so I mean, so you know where you get the largest outpouring of volcanism?
Yeah.
That's pretty impressive.
Yeah. Yes, he found enrichments there, but they're much lower.
So,
yeah. So it's only in these volcanic plugs that are really the highest, like 1,000 ppm. So the concentrations. Yes, Bradley.
What's the tectonic setting for the big one in the edge of Mongolia? Is it rip setting? Rigid?
Yeah, I think so, but it's pretty dodgy. It's pretty hard to put together. It's a bit of a mess. But yeah, I think it was a rift.
So the interesting thing about peak ranges as well is that they found that there were 2 ages of organisms that were attended in use of plant. So potentially there's a first phase which is then smashed by a second. So the age progression isn't clear for that province because there's so much, it's a broad range.
Yeah,
And you don't find that for some of the other regions along the track. So maybe
that's the magic.
something in-
yeah. I mean, obviously, if you really want to fractionate these things like crazy, you want to keep dribbling in magma, keep it going,
Yeah.
and allow you to really crystallize out the compatibles. Michael couldn't help himself.
Yeah, so I think the point you had on the magmatic hydrothermal transition earlier is very important to context because like when we think of all systems, magmatic system, we have fusion, it cools down or decompresses, then it bubbles. Inside the liquid magma, so you have liquid silicate magma with bubbles of H2O, and then that H2O will partition stuff into it, and then those fluids will go somewhere and make a deposit. And then you have a separation between, like we have a port we plug in here, and the fluids came out over there and made a deposit. That's not how it works in carbonatites, because in there, first of all, when you say carbonatite rock, it's never the liquid that made it, right? Because in the experiment you showed, I started with a mixture of everything. So it had calcium, magnesium, iron, phosphorus, fluorine, chlorine, had the periodic table. Then when you put it down slowly, you have a zone of calcite, almost only calcite. Then a zone of almost only dolomite. Then a zone of other things. So they're very effectively separated. Okay. Now the other thing that as it was cooled down from 1200 to 200, there was never a stage where it dissolved fluid. So it was at the beginning, high temperature it was melt, then at the end it was blind. Okay, it was H2O with a lot of things in it. In between, it was always just one phase, and you say that those faint lines, so it's a blind melt. Right? So it never had this case where it had bubbles coming out of it. Sometimes you do because in natural systems it will happen because of the decompression, but those bubbles are not pedagogically important because they will not partition into them. So a mineral still remain inside the metal, the blind metal, blind that is directly for the carbonatite. It was never a separate thing. So then when you have fluids that you can are those actual fluids in the classical sense, or is this just a carbonatite that became a fluid? So then this is not fluids coming off of carbonatite, it is percarbonatite, which I think is a very important thing. The other thing is that something that keep forgetting about that carbonatites are extremely reactive. So if you think of a circle, you put it in a bucket of silicate melt, nothing will happen to it. If you take a circle and put it into a bucket of carbonatite melt, it's gone in 10 minutes of time. So they're very reactive. So whenever you see carbonatite, the rock that you see is a combination of the cumulate processes happening within the carbonatite melt itself and the reaction with the rocks around it. And I think those are some of the things that make it just so hard to understand what's happening there. Like, okay, I'm looking at the rock, it's not an andesite. It's this whole sum of processes that we don't understand.
Okay.
Yes. Yes.
That depends if we're above the critical point or not. But yes, it's a very good point. Okay, with that, I think I will stop.
Okay.
Thank you.
Thank you.
Yeah.
Got some applause from, and thanks from online as well. Look at later. Thanks everyone.